So Pradeep, right, like you have seen many of the technology revolutions from the PC to client server to the internet, then cloud, and now AI, right? Like tell me what was the inspiration to start Juniper Networks? Let's start with the internet era.
Well, that was a long time ago, but I think inspiration there was, Naveen, that I was looking for a problem. I'd been at Xerox for about 12 years at that time, Xerox PARC, and I was looking for a problem that was both hard to solve, but also mattered to a lot of people. And in looking for that problem, I noticed something. This was 1995. So what I noticed was, the bandwidth was increasing, literally doubling every 6 months, no matter how you measured it. Number of servers, the amount of bandwidth, the number of websites, et cetera. That was one thing easy to notice. Second thing that was easy to notice was that the cost of long-distance bandwidth had been falling exponentially. And that was a big reason why communication wasn't as fast as it could be. And then in the middle of those two things was a gap, which was that internet routers were built using general purpose CPUs. And so this smelled of opportunity. The problem was hard. Building routers was not easy. And so these are the insights that led to the founding of Juniper.
Got it. And remind us, right, like people talk about like in today's world, 0 to 10, 10 to 50, 50 to 200. What happened during the internet days, right? Like how quickly did a hardware company scale?
Oh, good Lord. I think, let's see. The company was founded in February 96. 1998, August, we shipped our first machine. This is a new silicon, new operating system, new routing protocol, new everything. And the team size when we shipped the first machine was 43 people.
Wow, including silicon.
Everything, okay? And in the very first year, we sold 6 million. Next year was 100 million. Year after that was 400 million. Year after that was 1 billion. So it was at that time the fastest growing tech company. So the internet just basically exploded. And the reason was the timing was exquisite, even though I didn't realize it at the time.
Got it. Yeah, I remember it was known as the company which powered the internet. And you essentially leapfrogged all the other people, right?
That's right.
So let's move to this era, right? Like basically you have seen the internet, you saw the cloud, you saw the mobile. Now it's the AI era. So what excites you about it, and how's this different because you're still going?
Well, so what's what's funny is when I first joined Carnegie Mellon, way back when, too long ago, it was to study artificial intelligence because that was one of the centers.
Yep.
And as most of you know, AI has been through multiple winters. But I think advances in the underlying technology, particularly the amount of computing available, have made it now possible to do magic. And it's what I find stunning is the speed with which improvements are happening. There is no technology like it, but both in the speed of adoption and also in the rate at which improvements are happening. And improvements are happening literally in algorithms, in the architectures to run these algorithms, and in the work that these LLMs particularly are being put to, the applications. So at all levels, there is innovation. And one thing it is worth saying is that in the age of AI, one should remember that without the precursor technologies, this would not be possible. In particular, advances in silicon. There is no way we could do anything like this, number one. Number two, without something like the internet, it would not be possible for example, OpenAI to reach, what is it now, 600 million consumers?
More.
Maybe more, in the space of a year and a half. So this reach, this incredible reach, is possible only because of precursor technologies. But it is a remarkable phenomenon.
And like you've been a pioneer, right? Like in systems, hardware, and silicon. And I think you and I talked about this 7 years back. We might be entering the golden era of silicon and hardware. So tell me more, and then we'll go into the plateauing of Moore's Law or the end of Moore's Law. But let's start with, why is this the golden era of systems?
Well, it is the golden era of systems. The thing that is, Naveen was kind enough to be the first investor in my startup after Juniper. It was called Fungible. And it is both the golden era of silicon, but also it's kind of a difficult thing to execute simply because there is incredible concentration of customers. Mm-hmm. And anything that involves silicon and systems is expensive. It's expensive as heck. Naveen is one of the rare VCs who has patience. And if you don't have patience for investing, there's no way you can actually succeed in building a silicon-based or hardware-based, a systems-based company. I can tell you that in AI, the biggest gains will come from vertical integration, where there are people who understand the algorithms, they understand the software layers, they understand how to map it onto the silicon, and if they can, and of course, the systems that connect and the networks that connect all these things together. Anybody who understands those layers, and it's very, very hard to find people like that. Mostly people stay confined to a given layer. But when you can look across these layers, you can get literally factors of 3 to 4 in each of these layers. And so there's a multiplicative effect. And there's also learning. And what I'm waiting for actually is, if it hasn't already been applied, is to apply AI to improving the systems design itself.
Yeah, let's find a company then.
Yeah, well, that's escape velocity at that point. It's not reversible at that point.
Got it. I think a lot of talks or the progress has been beyond the CPU and the rise of accelerators. How did it happen? Because the world was saying software is eating the world, general purpose CPUs are the way to go. So you did it in networking, right? You guys had custom silicon in the 90s, late 90s. So what happened? How did NVIDIA rise, and what led to the fall of the x86?
So I think, this is, there is a view amongst people, particularly who write software, is that software and hardware are sort of antagonists. And this is incredibly far from the truth. Okay, look, long time ago, maybe 70 years ago now, this magical thing called general purpose computing was invented, Turing-complete machines. And by the way, it doesn't take very much machinery to become Turing-complete. So the only question is, how can you implement this thing fast? And over the next literally 40, 50 years, some of the cleverest people on the planet started to optimize the designs for general purpose computing. And general purpose CPUs are magical because you can write almost any application on it. But we got compounding gains from Moore's Law, just from the technology. Well, the technology flattened out sometime in 2002 in terms of clock speed increases. And this is why multi-core CPUs were invented. But the one thing that general purpose CPUs depend on is very high performance single-threaded computation. Well, that ship has sailed, and it's not possible to improve that particular thing given the physical and logical constraints of computing. It's just, so many people have tried. In fact, when I was looking to found Juniper, looking to start a company, I thought about this problem, and I said, better stay away from it, because even back then it was visible that this was a hard problem, and technology is going to carry it to a certain point, but then no more. So what you are seeing starting about maybe a decade ago, is the emergence of application, not ASICs. It is workload-specific machinery. GPUs, NVIDIA landed in a very nice place because they had this machine which did, designed for graphics, but it did vectors and matrices very well. And it turns out that it was extremely well applicable to machine learning computations. And Jensen has done fantastically well to actually recognize this. And he was developing CUDA back even before, I met him in 1995, before founding Juniper. Even back then, he was talking about this. It wasn't called CUDA back then, but he said, hey, there is this language, C-like language for parallel computations. And he had this vision back then. So it took a long, long time to develop this platform. So I think the same phenomenon that you see for GPUs, which is, let's just call it vector floating point or matrix floating point computation acceleration. The premise behind Fungible was also that there are other such computations in the data center. The moment you make it scale out, and so we invented this thing called the DPU, which accelerates things like networking, endpoint, security, and storage applications. And that acceleration is about a factor of 20 compared to general purpose CPUs. So this is why this technology is getting embedded now universally across Microsoft Azure and also potentially in AI networks in the future.
Great, great. So we know, right, like you talked about workflow specific or workload specific processing. So where are the opportunities in the AI hardware stack above and beyond the accelerators? I know like networking is a huge bottleneck, like people are processing, but connectivity, both at the physical layer and the IP layer is an issue. So where should people be trying to find the next Juniper, the next NVIDIA, right? Like where is the bottleneck now?
There are many bottlenecks, but let me start out with the biggest one. I think the biggest bottleneck is memory bandwidth, both the capacity
so I/O.
and I/O. So I have a compute engine, and we are entirely limited today by the periphery of the device. And so people are innovating, TSMC particularly, in 3D and many, many layers to improve the bandwidth coming on and off the chip. That's number one. Right behind memory bandwidth and memory capacity is the network bandwidth. And in sharp contrast with previous networks, which were more general purpose, IP, Ethernet, et cetera, these networks, it's probably better to call them interconnects because they've been stratified into like almost three, maybe four different bandwidth latency domains. There's a scale-up network that connects small number of GPUs at very high performance, a few hundred. Then you have the scale-out network, which connects in the building maybe a few 100,000 GPUs. And then there's a scale-out global network, which can connect millions of GPUs across the wide area. And because performance per watt is the metric, every one of these domains has to be squeezed and optimized. This is different than the situation in general purpose networks. And so one big problem is that there is a gap in the use of copper for the scale-up network or interconnect and glass. There is nothing that addresses the problem well between about 2.5 meters and maybe 20 meters. So this just happens to be...
So that's the copper or active copper.
Active copper will take you maybe 5 meters, but not further. And you need to address... So right now, the number of GPUs in the highest performance domain is not limited by switches. It's limited by this physical interconnect. And people are working very hard on this, and I know that the problem will get resolved eventually. But that's an opportunity. But it's an opportunity where you have to combine physics with electrical engineering. And so it would be a special kind of startup.
Great. We'll go find it, right? Like, so there are many people here who come from the tech industry, probably primarily they might be buyers of technologies, builders of technologies. So you went through the journey of being a serial founder, but first time you were a technologist, amazing architect. What were the things you would tell yourself when you were starting a company today? So when you make the leap forward from being a technologist, whether head of Eng, director of Eng, an engineer, an architect, how do you go about doing it? What would you tell your younger self?
Well, I was incredibly naive when I started. And if I had known all the difficulties up front, I probably would not have started. So naivety is good, in a sense, because if you saw all the difficulties that would face you, you wouldn't get started. So some of the learnings, one is that as you scale a company in terms of number of people and number of products, things get more and more and more complicated. And you have to learn to delegate. You can't do everything yourself, by far. You have to surround yourself with the best people you can find. There is no substitute for that. I think this idea that I can conquer a problem by hiring masses of people is, in my opinion, foolish. You need to have small teams, agile teams, especially today, with the opportunity of doing things in a different way than were done before. You need people, highly intelligent, driven, motivated people. So as a founder, if you can surround yourself with people like that, you'll do well. By the way, one thing I will say about ideas and startups, you can find great teams, you can have a good idea, but if the timing is wrong, there's nothing you can do about it.
You can always pivot.
You can pivot, but pivoting is extremely expensive and frustrating for the team and for VCs particularly. So if you can land on an idea whose timing has come, it's magic. And this was the case with Juniper, by the way. As I said, without realizing it at the time, had the company been 6 months later or 6 months earlier, it would not have been the company that it was.
Got it. So let's switch gears, right? Sorry, you had a question? Yeah.
There was no pivot. Honest to God, look, in the beginning, Vinod, asked me to talk, Vinod Khosla asked me to talk to advisors. They all suggested, oh, look, why don't you focus on enterprise networks? And there is IPX, and there's SNA, and there's all these other things. And my founders and I stuck to our guns. It's IP, the internet protocol. That's the right thing. It's the only scalable networking protocol known to mankind. It still is. So we stuck to our guns.
Oh, that's great. So talk a little bit about, there's a lot of hype about AI. We might be early in the cycle. What do you think is not being talked about? 10 years out, what do you think happens that most people may not know about?
I mean, it's impossible for me to see even 5 years out. 10 years out is...
But where do you see 5 years out or 3 years out? What happens? This is like a utility everywhere?
I think, first of all, we will keep making advances in the cost of computing for AI.
That's where I was going.
Particularly inference.
Yep.
There's just extreme... It's too expensive right now.
Yep.
Everybody
so where
knows
does it
this. I think the marginal cost is going to be very small.
So you think it'll be a utility, like we get electricity, like everywhere?
Think back to the days of electricity in the beginning.
Yep.
And then in the beginning of the internet, things were very expensive, right? Mm-hmm. And as the volume grows, people learn how to do things better, it'll come down. And one of the things that was surprising was, take Cisco and Juniper as the two companies. Initially, we were enjoying 95% margins, okay? But as more and more people started to build those things, those margins today are probably around 50%, if you're lucky, because things tend to get commoditized. And so companies that are riding high today may not necessarily do so in the future.
Got it. For the people in the audience, right? Like, how do they endorse this technology in their daily use, right? This is going to be everywhere. Should people be afraid of it, or say like, hey, I'm the jockey, ride this horse, like we did? So any, right, like advice for people on how to use this stuff and how to make it part of daily life in both work and personal settings?
I think, the analogy I give to my children is that long time ago, humanity came across reading and writing. And there were people who probably poo-pooed that as well. And it made a sharp dividing line between people who could use that technology and people who couldn't. Folks today who ignore AI and poo-poo it are going to be left behind.
Dinosaurs.
They'll be dinosaurs. And so if I were growing up today, I would apply myself 120% to figuring out how this thing can help me do things better and faster. I think speed is always valuable. That is, the time that it takes humans to do something, it's always valuable. And this thing is an incredible tool. The one thing I will say about it is that almost all the LLMs, at least, have been trained on an abstraction of the real world, not the real world. And there's a lot of talk about AGI, et cetera, whatever that is. You're not going to get to it without being trained on the real world. But so we must never forget that these models have been trained on abstractions, not on the real world. So until we get to the point where they're also, have a complete understanding of the laws of physics, similar to what children do, without actually being able to articulate Newton's first and second laws, et cetera. There'll be gaps, but it's good enough to use for many, many things. And I think the trap to avoid is to become lazy. It's quite easy to become lazy. So I think that's the careful walk one has to do.
So I think, Pradeep, like we started a little bit late, and the next panel will be coming, but a lot of you guys requested to get some time in the hallways if you want with Pradeep. So please join me in thanking Pradeep for taking the time. It's an honor to always work with you.